All right, in this video, I will work the questions for demo number 1, lesson number 7 on correlation and regression. So let's get to it. I'll tell you what, I have up over here, so let's take a look at make it available. All right, this one should be pretty quick. You can see that I've already done these, so I don't have to worry about typing in the numbers and a typo and things like that. Um, So it looks like we need to construct a scatter plot with first weekend gross on X and US gross on Y. So I'm going to pop this stuff into StatCrunch. Easy for you to say. And let's close that down. Okay, so I want to go to graph, come down to scatter plot, and I want first weekend gross. Okay, something's going on here. What's going on? Okay, this is not cool. So what they've done is they've actually brought in on the data the the title first weekend, so the name of the variable. So that's just totally uncool. So we need to take care of that. All right, and then of course I need to delete row 1. So I'm just going to go to edit, row delete. Calculate that and compute. All right, so now we've got something that we can work with. So that was weird. You don't see that happen often. So again, let me refocus, do a scatter plot. So we want first weekend on the X, and we want US gross on the Y, and hit compute. So I'm looking for the scatter plot that has, these, I kind of have focused on these 2 points. Clearly, I don't think A, and it turned out to me the B seemed to be the closest. The next thing we wanted was first weekend and then worldwide. So I'm just going to go up here and edit and change worldwide gross. And again, I'm looking for the one that looks most similar, and I thought B looked most similar, so I selected it. What can you say about? I don't think we need this anymore. What can you say about the relationship between first weekend gross and US gross? Well, I chose this one, I selected this one. There appears to be very little relation because I don't see a linear model really fitting either one of these scatter plots very well. So that's what I chose. All right, question number 2. So we have some more information here. Looks like we're looking at the relationship between GDP and social media and internet usage. So let's open it in StatCrunch so we can do something with it. I'm going to check to make sure that something wacky didn't go on like it did before. That was really strange. You don't see that happen very often. So what we want to do here is we want to scatter plot with GDP. So again, I'm going to go to scatter plot. I want GDP per capita on the X, and I want social media on the Y. So hit compute, and the one that I thought looked most like this was D. Now notice that the axis is off a little bit because our axis here starts at about maybe 55, and their axis starts at about 0. So what I did is I just tried to focus on where 55 would be and focus on that. And again, I selected there appears to be no relationship because a linear trend would have a positive, negative, linear relationship that would be represented by the cluster of data points. Construct a scatter plot. Let me go grab that again. And so what I want to do here is I want to put internet usage on the Y. And see, I do see a linear trend here. And I selected C. To me, it was kind of a close between B and C, but that one point right here where I'm circling kind of made a lot of difference for me. So it seems as though, because we do have a linear trend and a positive trend, I selected that as GDP per capita increases, so does internet usage. All right, this question gets into something called extrapolation. And extrapolation tells you, defines a property that says that if your model is built on a range of X values, then predicting anything outside the range of values is inappropriate. It's kind of like if I went into a nursing home and collected data on, 70, 80, 90, 100-year-old, maybe even. I wouldn't want to use that model on a bunch of kindergartners. It wouldn't make sense. The model wasn't created for that population. So what we have here is we have a straight line was fit using y hat equals 3 plus 5x. The values of x that were used to create this model ranged from 3 to 28. So what that tells me is it is inappropriate for me to make a prediction based on anything below 3 or above 28. So should the model be used to when x is equal 4? Yes, 4 is between 3 and 28. Negative 4, no. Negative 4 is not between 3 and 28. 0, no. Same reason. 27, yes, because 27 is between. So that's an extrapolation problem. So fitting a straight line to the data set. So we have that the predicted value is equal to 20 minus 0.2x. So the y-intercept, what the y-intercept tells me is when x is equal to 0, my predicted y is going to be, in this case, 20. So the interpretation here that I chose, that I selected, is the y-intercept b0 equal 20 implies that when the value of x is 0, that the mean value of y is equal to 20. That's one of those little caveats, so we just have to tattoo to the brain. The predicted y is actually the mean value of y. So when we predict something, I don't want to get too scientific here. I teach a graduate level class in regression. We get into all the distribution of the y sub i's at every x sub I and error variance and all those different things. I don't want to get into that in this class because this is an intro class, but just I guess it's one of those things, even if you don't understand it, just tattoo it to the brain. The predicted y at a particular value of x is really the mean value at that y. Let me do a little bit of teaching here. I don't want to just throw this under the bus and forget it. Let's say that I was predicting first year GPA from ACT, okay, for Shawnee State University students. If I have an ACT of 26 and I collect data, is every single student that scored 26 on the ACT going to score the same first year GPA? Yeah, it's not even reasonable to think that. There's going to be variation in those responses, in those first year GPAs, right? Well, my model would predict the average of all of those GPAs at that particular level of ACT equal 26 in my illustration or my example. So that's what's going on here. We're predicting the mean of this distribution of y's that are actually predicted from a set level of x, in this case, a level of 0. All right, interpret the meaning of B1. B1, in my opinion, says as x increases 1 unit, the predicted y increases whatever the slope is. In this case, it's negative 0.2. The closest interpretation that we have there is that implies that for each 1 unit increase in x, the value of y is estimated to decrease 0.2. Now for this, predicted being x equals 6, let me pop that in my calculator real quick and show you what we do. All we do for this problem is just put 6 in our model. So I'm going to type 20 minus 0.2 times 6. And let me show you what happened there. And you can see that's what happened. All right, so 18.8 is the predicted value. All right, next question. All right, next question, we have another data set, so let's open it up. So it looks like we're looking at tuition per year and mean starting salary. That's kind of interesting to me. I have one daughter who's going, I have two daughters who are both seniors this year, and there's 35 days difference in their ages, by the way. They're both adopted from China. We adopted Sadie when she was uh, 15 months old. We adopted Bailey when she was 2.5, but there's only 35 days difference in their ages. So anyway, long story short, they're seniors in high school, so they're going through this whole college admission thing, and they just got accepted. Well, they got accepted a lot of places, but Sadie will go to the University of Chicago in the fall, and Bailey will go to the UK Honors College, University of Kentucky Honors College in the fall. So the reason I share that is we're smack dab in these numbers right here. So construct a scatter plot. So let's do that. So the x variable. Now what I do here is I have to read the problem, and the problem says right here. I wish I could highlight. Yeah, right through here. Examine the factors that impact starting salary and decides to develop a model that uses program per year tuition as a predictor of starting salary. So that tells me that the predictor here is program per year tuition, which tells me it's the x variable. So I want to use that to predict mean starting salary. And I want to look at a scatter plot. Well, clearly, I think D is the one that aligns with that, so not a lot of debate there. Now, assuming a linear relationship, determine the regression, estimated regression coefficients. So I'm going to go to STAT. Again, I've taught all this in a previous video, so it should be no surprise. And once I get this output, there are a couple of ways that I can get my B0 and B1. First of all, I can get it from this line right here. So the number without the variable is the intercept, which you can see I typed in for B0. And the number with the variable is the slope, which you can see I typed in for B1. Another way of getting that is in the parameter estimate table. Whatever is with the intercept is B0, and whatever is with the slope is B1, right? And then you get something kind of cool here. You get the scatter plot with the line of best fit, although we really don't need that. So let's get rid of that. So interpret the meaning of the slope. So again, for each increase in $100, the mean starting salary is expected to increase by $239. Typically, that's a little confusing because typically the x is increased by 1, but they decided to increase it by 100, which tells me I have to multiply this by 100 to get 239. So the predicted starting salary will be 8132 when the first year or the per year tuition is 38,983. Let me show you how I got that. So I have minus 11616 plus 2.39 times 38,983. And let me pop over here and show you how to do that. So be careful up here when you enter this negative in front of the 1116. You have to use this one down here, the one below the 3. You can't use the subtraction because the subtraction has to be subtracted from something. if you're assigning something a negative value, you have to use that key right there. So just, just as an example, if you use this, whatever it was, well, shoot, it gave me the, I don't want that. I want just minus. Well, anyway, take my word for it. It's not going to work if you do. Let me get this off so you can see the output. All right, so the predicted salary, 81,362. Now, that was off a little bit, wasn't it? If let me explain that. If we go back to our I'll tell you what, I've got it up here, don't I? Now, if I type in negative 11,615.889 plus 2.3850967, and then multiply by the 38,983. Notice that I get the correct answer. Now, I didn't before. Why? Well, up here, let me get something to point. Up there, I just took the values that I have over here that I entered as the answer, but I entered these according to the way that they wanted me to round the answers. But those aren't technically B0 and B1, they're just B0 and B1 presented per the rounding instructions through my stat lab. But if I'm actually going to calculate the predicted value, I need to use the decimal expansion of, and let me go up and show you that, I typed the, it's kind of clumsy. I typed the 2.38. Notice how I typed the slope all the way out. Well, when I did that, I got the correct predicted mean salary. So, rounding really matters, obviously. So what insights can be obtained about the relationship between program per year tuition and starting salary? Well, we clearly have a positive slope, 2.38, 2.39. And so that tells me I have a positive relationship, and a positive relationship tells me that as per year tuition increases, then the predicted starting salary upon graduation increases. So the one that corresponds with that is B, mean starting salaries upon graduation tend to be higher among programs with higher per year tuitions. Now, just an FYI, if the slope was negative, we would say that mean starting salaries upon graduation tend to be lower among programs with higher per year tuition. But that's not what happened here. All right, next question. There is no next question. All right, that finishes this demo. Take care.